Okay, so welcome all. This is the pattern recognition lecture. We'll meet throughout the semester once a week. I will start by giving you an introduction of what pattern recognition is, and then we will take first steps today for you to see if you like it or not. So first of all, I would like to thank my group. My name is Hamprecht, and I have the pleasure of working with these pleasant and professional people. You will have noticed that we are not on campus. The reason is that when we founded this Image Processing Institute 3 years ago, there was not enough space on campus. So we're now 5 groups altogether, and we had to find well, big enough space for us. We work with a couple of industrial partners, and we got some money from the Excellence Initiative, allowing us to do our work here. So, what can you do with pattern recognition? I've given a very incomplete list of possible applications. So industry is interested. For instance, if you buy, let's say, your mobile phone, you want to make sure that there are no scratches on it. And nowadays you don't have human controllers, but you have cameras and computer vision algorithms checking your devices. So there's quality and process control. It's more and more coming into the normal cars that people drive. So for instance, cars will learn to brake by themselves. It's still better if you take control, but if you're about to hit a pedestrian, for instance, the cars will put up the cover above the engine so as to soften the impact with the pedestrian. Your car will also tell you when you depart from your lane, for instance. When you have a small shock, it will decide if actually the airbag should be fired or not, because an airbag, when it inflates, it can also really hurt you, so you really want to only inflate it if you absolutely have to. Then I think we have many physicists here. So in high energy physics, you generate tons and tons of data, and you don't want to sift through these by hand. So the distinction if something is an event or is background, that is accomplished by means of pattern recognition. Astronomers now acquire in their surveys huge amounts of images, and groups in Heidelberg, for instance, are interested in finding gravitational lenses. So you can use algorithms to sift through these zillions of images and find vestiges of such objects. My group, we work a lot with biologists, helping them with UHT, stands for ultra high throughput experiments, or we work in the neurosciences. Pattern recognition is used in medicine to decide if somebody has a tumor or not, for example. Banks use it to find out whom they should how much credit they should give a person. And then there are all kinds of security applications. More old-fashioned ones like identifying fingerprints in large databases, but also finding suspicious luggage that's been left somewhere at an airport, and so on. So overall, people have been trying to get more data for decades, and now we have the sensors, we have the data, but it's becoming a burden, and this is where pattern recognition methods help. I'm showing a few examples from my own group. Disregard all the small print. I just want to give a flavor of the kind of things that can be done. For instance, we work closely with the Bosch company in laser welding control. So you see a laser gun here used for welding, and then very high-speed cameras, and then we automatically decide if a welding has gone all right or not. Here's an example that was joint work with the German Cancer Research Center, where we looked at magnetic resonance spectra and decided if people, with what probability somebody had a tumor in the prostate or in the brain. We're working with people from the neurosciences. They have gigavoxel images, and we try to decompose these images into all the neurons. Here's an example from mass spectrometric imaging, also a high-dimensional type of data. In this case, you have a full mass spectrum for each and every pixel of the image, and you then can use pattern recognition techniques to help you delineate the boundaries of a tumor, for example. Now, I will give you more details on these approaches as we progress through the semester. I want to show you one interactive pattern recognition application that we're working on. Well, both because I like it, but also because I hope it is instructive. What this allows you is to train a pattern recognition algorithm by using just mouse input. This can only solve very simple problems, but it brings the power of pattern recognition to people who don't know about all the things that you're going to learn now. And these people still want to be able to use what I'm going to show you throughout this course. So what we have here is an open source program. I'm going to load some data sets. I will take my screen background because it's nice and colorful and I like it. These are tiny excerpts of a brain of, I believe, a mouse. And I am now going to use just the red, green, and blue values in each particular pixel. And the task now is for biologists to decompose this image into how much gray matter, how much white matter, how much background there is, because they want these measurements to normalize, let's say, some kind of wet lab numbers or numbers they got out of wet lab experiments. Now, you could certainly devise rules by hand to figure out what is background and what is gray matter, what is white matter. So, for example, if you want to find background, you would probably, design a question like, if the pixel is black, then it's background. If the pixel is greenish, then it's gray matter, and so on. And that would work for this kind of image because the colors already nicely discriminate the different classes of interest here. However, it would take quite a bit of fiddling with parameters. So what exactly distinguishes green from black? You would have to play a little bit. So if you use pattern recognition, I can just create a couple of classes here. Let's say I'm taking yellow for background, and I'm taking, let's say, red for that one here, and I already get some kind of prediction. And I'm taking green to mark labels, to mark a few pixels of this last class. Okay, and I get something that is, not perfect, but it looks approximately right. So now what's the difference between this colored image and the colored image we had before? Before, it was really just an image. These colors, however, they already represent class assignments. So in this colored image, the computer already knows that a yellow pixel is a background pixel, and red pixel belongs to this class, green pixel belongs to the other class. And what's more, I didn't have to invent any rules by hand. This becomes especially important when these rules are not so easy to formulate. So, for example, if you have just a gray value image, you cannot say if the pixel is green, then do this. You have to somehow start talking about what image processing people call the texture, because even in gray value images we can still discriminate different classes, but there it really becomes painful to devise something by hand, and this is where pattern recognition is very useful. So, what are the disciplines of pattern recognition? Pattern recognition, some people prefer to call it machine learning, has a couple of fundamental strategies or questions. One is how to visualize data. Then there's so-called unsupervised learning and supervised learning. All of them have the same aim of taking a bulk of data and extracting the information out of there to finally gain knowledge. Because you've seen knowledge is power, knowledge is money, and so on. So that's the interest. I will say a few words about each of these in turn. So visualization is very important. If you have, you should always look at your data to see if you find, something strange, unexpected phenomena. If you just have 2 features for each pixel, well, then you can just produce a scatter plot and look at your data this way. If you have 3 features for each object, you can still produce a scatter plot, and if you're on a computer, you can rotate this nicely, and this will give you a spatial impression. But if you have 4 or more features, it becomes a little bit tricky. And that is very common nowadays to have high-dimensional data. So not just 4, but have hundreds or thousands of features even. So if you have 4 features, something you could do is produce a so-called pair plot, where you plot the first against the second dimension, the first against the third, first against the fourth dimension, and so on. But you see that the number of plots rapidly inflates as your number of dimensions increases. I'm showing you a bit more advanced example here. People in Zurich made that one. What you see here is political trends. Each of these dots corresponds to a Swiss community, with the German-speaking communities being blue, the Italian-speaking being orange, and the French-speaking being red. And in Switzerland, there are a lot of popular decisions. So it's not the politicians alone that make the decisions, but people have to go and poll frequently on certain issues. And the result of these polls can roughly be classified as right or left, or more ecological or more technological. And what's shown here is an interesting trend, namely how from the 1980s to 2000, how the political scene changed. So you see that originally in 1980, there was, we will jump back to the beginning, in 1980 there was a big correlation between being left and being ecological. And over time this has changed, and now ecological arguments are more assorted with or associated with conservative positions. So we are here. We recently had elections in our federal state, and they seem to follow the same pattern. So our federal state is pretty conservative, and now apparently ecological concerns are have become an issue here. Now the raw data that went into this is it's a bulk of data, because it's thousands of polls, hundreds of communities, but using appropriate visualization techniques you can somehow turn them into a form that makes it easy to tell a story. So we will look at visualization further in the semester. This is now in more technical terms the list of things we're going to look at. Today I'm going to talk about the K nearest neighbors classifier. So if you walk away from the course after the first time, you will already have learned something. So I consciously picked something that you can use in isolation wherever you are. So K nearest neighbors is very simple, but a good method. We will then today start looking at a theoretical basis of more advanced algorithms. So we will prepare the ground for statistical decision theory. And then throughout the course of the semester we will look at dimension reduction, at neural networks, and lots of methods that today are thought useful and practicable. So the big picture then, to summarize, is that pattern recognition is, I think, the single most important development that has taken place in computer science in the last 2 decades. Because if you want to teach a computer something nowadays, you don't try to extract the rules that a human would use to make a distinction and then program these rules explicitly into the computer, but you provide the computer with some historical training data and you let the computer itself infer the rules, and if the computer is successful, it's going to be able to make correct predictions on further examples. This is really transforming, well, a couple of businesses, but also it is transforming the way science works nowadays. And I hope that by the end of the course you will be able to, when you read a paper, to understand what people are doing and give you access to more recent research literature. Okay, so we're looking at the K nearest neighbors classifier. I think we need some terminology at this point. You know, very basic terminology. By the way, both K and NN are unfortunately frequently used with different meanings in pattern recognition. So NN can be neural networks or nearest neighbors, as in this case. K can be a number, like here, or it can be kernel, and you have to always figure out what is meant this time. Now, in K nearest neighbor classification, you need a training and a test set, and it allows you, given the training set, to learn classification. So K nearest neighbors is a simple classifier. What is a classifier? A machine that predicts a category. So all of you have learned about regression, where you get some features or descriptors, and as a function of these descriptors you are computing a number that you think is the function of these features. In classification, you predict not a number but a category. So the difference between a category and a number is that if I have categories A, B, and C, it means or it does not imply that C is more than B and B is more than A. It just means different. Okay, like apples and pears. Some people like apples better, others like pears better. So it's just different categories without any ordering implied. Now we need a training set. And a training set is a collection of samples or training exemplars and in these each of these exemplars is characterized by features. I'm underlining all the technical terms here. And a label or a category. And the task now is, in any classifier, to predict the labels from the features. And machine learning means learning how to predict the labels from the features given a training set. Now, besides the training set, you typically have a test set on which you evaluate how good your method does actually. So this is another collection of exemplars using the same features and similar, the same labels. But the test set is not used for training, as the name implies. but to see how well you do. And this not using it for training, that's an important point, because you will see that sometimes pattern recognition methods have many parameters, and the temptation is great to use some setting of the parameters to train on the training set, to then see on the test set how well you are doing, and if you didn't like your results, to then change your parameters and do the same thing over and over again. And if you have enough parameters, you then implicitly overfit your method on the test set, well, overfitting means, yes, you're eventually going to do great on this particular test set that was applied, but you're going to fail once your method is really delivered and used in practice. So now k-nearest neighbor classifier, I could write a formula to explain what it does, but it's really most easily explained in words. So k-nearest neighbor classifier makes a prediction for each query just based on the membership of the closest point in feature space. So query can also be considered a technical term. Based on the label or the category, or sometimes also called the class membership. So this really leaves us with two questions, namely, how do you define closest? Unless you have smart other ideas, it's typical to just use Euclidean distance. It also leaves you with the question of what features are actually going to be discriminative or meaningful for your problem. But that question is general to all classifiers. And well, I've written k-nearest neighbor here, but another reason why I like the blackboard. I should have written one nearest neighbor here, because the one nearest neighbor method just takes the class of the single closest sample to make its prediction. And well, accordingly, if you use a number k greater than 1, it uses the k nearest neighbors to make a prediction. So for instance, if you say k to 7, then it finds the 7 nearest neighbors in feature space, and then makes a democratic vote among those 7 neighbors for what class is deemed most likely. So I'm trying to show the same here in terms of a picture. So let's say we have a classification problem. For example, this have a tumor or not, and we have some feature, I'm not giving any details here on what exactly that is, and another feature, and our training set consists of exemplars that are characterized by features and a label. So I'm also showing the label here that each feature has. And now in classification, you try, given such a training set, to infer where the decision boundary should be. So, it looks like on the upper right corner you're going to predict the blue class, and in the lower left corner the red cross class. But what exactly do I mean by upper right and lower left? And different classification methods give different answers to this question. Now, the answer delivered by let's say one nearest neighbor is as follows. The one nearest neighbor method, it partitions feature space into areas that are closer to one observation than to any other. So what you see here is a Voronoi partitioning of feature space, and if we're now asked to make a prediction, we just look up in which of these Voronoi regions we are. So if my query point lies here, the closest observation is this one, and I'm going to predict blue. If my query is down there, I'm going to predict red, and so on. And the decision boundary, by the way, in this case, is defined well as all these faces that lie between two different classes. So the decision boundary in this case would run along this line here. And it's a bit of a funny decision boundary, right? Because it has these steps. And other methods believe that, with such a small training set, do you really believe that your decision boundary has these funny steps here? Or do you think this is an artifact from having such a small training set? And indeed, many methods try to estimate smoother decision boundaries, and they inject this smoothness in different ways. Now, k-nearest neighbors also allows you to inject a little bit of smoothness. Can you suggest how? So if I'm going to make k large, is it going to be going to give a smoother or a rougher decision boundary?
It should be smoother, I guess, because you make more decisions, because you have more.
Yeah. So the answer was, if you make k large, then you get smoother boundaries. That is correct. I have not defined exactly what I mean by smooth, but we agree in any case. To give a concrete example, let's say if I have a single outlier of the red class somewhere in the blue, if I use the one nearest neighbor method, it would create a small island here. And if I use k larger than 1, the island will just be ignored. I think I have an example somewhere. So I have artificially generated 2 training sets. So the first training set is in the upper row, the second training set is in the lower row, and these training sets were generated from the same underlying distribution. So the training sets are absolutely identical up to the randomness that you have when you sample from some random process. And you see that they look generally the same. So we have the blue class here and the red class outside, blue class here and red class outside, but they differ in the details. So if I use the one nearest neighbor method, like in this first column, each of these actions creates a small island. And the island which was created in this training set is not visible in that training set, and that island is not visible in this one, and so on. And if we now choose larger values of k, like here we have the 21 nearest neighbors, it's still not identical, but you see that at least these tiny islands have disappeared. And if you look at it more closely, you will see that the biggest differences are somewhere here in this corner. But you have to keep in mind that in this area we do not have many training samples anyway. So you see the density of points is much higher here. So the decision boundary that we get matters more here than there, where we have fewer samples. Okay, so the one nearest neighbor makes its predictions for a query based on the class membership of the single closest sample from the training set. K nearest neighbor uses the k closest neighbors. So I have a couple of comments on the properties of this method. So I think you will agree that the method is extremely simple and performs, I will claim it performs well. Now, the people who make a living out of producing pattern recognition algorithms, they will say, no, it doesn't do well, we have much nicer methods, and that is true. But, compared to having nothing at all, it's actually not such a bad method, especially in low dimensions. it also illustrates the importance of having training and the test set, because the empirical error on the training set is 0, as long as we do not have two observations of different classes in the very same spot of feature space. So what do we mean by that? If I train, in quotes, a one nearest neighbor method on so the empirical training error of the one nearest neighbor classifier. If I train a one nearest neighbor classifier on a training set, and now I try and make predictions drawing samples from the same set, I will of course get the perfect answer every time. So in other words, I have learned the training set by heart. And this gives no indication of how well we're going to do in the future, because when we have some overlap between the classes, as you saw in this example here, you see there is some overlap between the blue and the red class. So you don't have any hope of in the future making predictions that are correct all of the time. So essentially, this just stresses the importance of having a separate training and test set. It has relatively low, it has jagged boundaries, as we discussed, and the method has a low bias and high variance. I'm stating this more for future use, because we're going to discuss in the future what bias and variance actually are, and then when you go back to your notes you can see that, okay, one nearest neighbor had a low bias and high variance. Now in two words, bias measures the deviation a method has from the optimum method, the deviation caused by the method being too stiff, and one nearest neighbor, you know, it's a flexible method, so it has low bias, but its results can vary a lot as you go from one training set to the next. This is an undesirable property called variance. It is a let's say it's a lazy learning strategy, in the sense that you do all of the work at predict time. At learning time, you really only just store the training set. You don't need to do any computations. It's only when you want to make a prediction that you have to start looking for the nearest neighbors. So training costs 0 time. A prediction can cost a long time or a lot of time if you have a large training set. So generally a large training set is desirable, but here it means that prediction costs of the order of n, where n is the number of samples in your training set. There are a few tricks to get there faster, for instance using approximate nearest neighbor search, but these methods they tend to not do so well in high dimensional data. So you can use KD trees and similar, but you get the biggest savings for those only in low dimensions. As I said, there's still the question of how do you measure proximity? What is a good similarity measure? And this is your chance to inject prior knowledge. So if you know what the features are, you can define or at least scale your distance function accordingly. All of that. So classification methods, if you give them a lot of features, they can tell you which features are more informative than others, but they cannot tell you what features to compute in the first place. So, we talked about this tumor example, and I just said it's feature 1 and feature 2. Classifiers do not tell you, what features you should measure in the first place. So whether you should measure some antibody in the blood, or if you should take an MR spectral measurement. However, having the right features makes all the difference. So I'm showing an example here where it's pretty hopeless to try and train a classifier because there's too much overlap between the classes. These features were not discriminative. And now I introduce a magic bullet here, the fantastic third feature that now allows you to see that really the classes do separate in space. So actually the image I've shown on the previous slide, those were the exact same coordinates, but omitting x3, so projected down onto the x1, x2 plane. And getting the right features, this is a matter of domain knowledge. So you cannot read about it in a pattern recognition textbook, but you really have to understand the experiment and decide what measures are probably going to be helpful in discriminating your classes. In this sense, much of the art of applying pattern recognition techniques is finding the correct features, and you could say with some justification that all of image processing, or let's say much of image processing, is just about finding the right features to then finally use your classifier on. Okay, now there have been a couple of modifications that were proposed. For example, people proposed editing methods. In editing methods, you have now all the liberty. For example, there is a method called condensing, which works as follows. So condensing is defined as follows. You iterate the following. You select a training sample, and then put it in an active set. And then you have a loop over the samples. You check if a given sample is correctly classified by one nearest neighbor method on the current active set. So, if the current sample is classified correctly by the one nearest neighbor method on active set, then you just discard it because it's deemed non-informative, and otherwise add it to the active set. So this method, unfortunately, is order dependent. So condensing is order dependent, meaning that if I take the same training set, but I sample a different exemplar here randomly in the first step, I might end up with a different classifier. So that is bad. But on the other hand, what's good about it is that in a sense it keeps only the informative samples, and in that sense also it is similar to the so-called support vectors of the support vector machine, a classifier that we're going to see a few weeks from now. So as I said, k-nearest neighbor is a nice method, but you probably now sit back and say, yeah, it sounds a little bit ad hoc. So especially if you look at modifications as this one. So it speeds up the whole procedure because the active set is much smaller than using the full training set. But what is the price you pay for this modification? Or if you think of other modifications, how are you going to know if it's good or bad? And that is why we're interested in a more principled approach also to understanding the pattern recognition problem. And this is the subject of statistical learning theory that I think we will manage to study before the day ends. So I hope you noticed that this was motivation for the next step. But before we take that step, I want to make one more comment on the features, or on the proximity measure rather. So one proximity measure for the k-nearest neighbor classifier that is very successful in image processing works as follows. It is called the tangent distance, and if you take, it works. So basic ideas. You have two samples. You want two high-dimensional vectors, and you want to estimate the distance. You could either do that by just computing the Euclidean distance, or you could submit both vectors to the transformations that are usually observed. What do I mean by that? These are transformations which change the position in feature space, but do not change the semantics. For example, if you want to build a speech recognition system and you want it to recognize the spoken number 3, you want to be able to recognize it no matter if somebody said 3 in a low voice or in a loud voice or in a high voice or in a in a bass voice. So these are transformations that you want to maybe also learn in your procedure. And one way of taking care of these transformations is to build them explicitly into the distance that you compute between two samples. This was originally introduced in image processing, where it is very successful. So I think I have the table somewhere. This is an example. In this case, the task is to recognize a written letter or a digit. So I believe all of these are 5s written by different people. And nearest neighbor method, just using these raw observations, has an error rate of 5%. And if you use the tangent distance that I have just described in the briefest terms, you get down, well, you halve this error and you arrive at human performance, which on this training set is also something like 2.5%. If you want to know more about that, you can look at a script that I've started to write for image processing, which you will find on my homepage. That is not strictly part of pattern recognition. Okay. Do you have any questions for the k-nearest neighbor method?
You always took even number of nearest neighbors?
No, I think in all the examples I hopefully used odd numbers.
Yeah. Why?
Well, simply, let's say if we take, so the question is, why do you always use odd numbers in a k-nearest neighbor classifier? So if I use 10 and I find 5 samples voting for tumor and 5 samples voting for healthy, I don't know what to do. So this is the only reason. So if you have more than 2 classes, then just having an odd k does not guarantee that you're always going to get unique decisions. So let's say if we have 3 classes, I could have a vote of 3 versus 1, and I still don't know what to do. But that is the reason why we use odd numbers usually.
Another question can be, for example, when I want to decide a value for a pixel, for example, and I have 8 neighbors in a matrix, and I want to decide the middle value from the center, and in this 8th value I had 8 for red pixels and 4 green. What I must do to be correct decision?
Well, this is the same question basically. So what do you do if you have an even number? In that case, I would hope that there is also an observation of the central pixel, and I would take that observation into account also. But since you're talking about, you were talking about neighboring pixels and so on, so you imply that you're looking into an image processing context, and if the task is to denoise a picture or to smooth a picture, there are dedicated methods that do better than k-nearest neighbors, so I wouldn't use that in the first place. Okay, so let's have a 15-minute break, and then we will look at basics of probability theory.